let's go over how to differentiate and integrate a power series. So we talked about this when we went through the textbook, but I wanted to go through it again in detail so that I can also address some things that might confuse you. Okay, so here's the theorem. First thing to remember is that this theorem strictly applies to power series. Not that you can't differentiate or integrate other types of series, but they would have their own separate theorem. Okay, so here's the general form of a power series centered at A. It has a radius of convergence that's greater than 0, so it's not the trivial case where the power series only converges at its center. And if you think about why this has to be the case, because if it only converges at one point, then how could it be differentiable or integrable, right? For like a derivative or an integral, you need a series of points, not just a single point. So the radius of convergence is greater than 0, and it's either a finite interval or from negative infinity to infinity. So with that, since it's convergent over some radius, we can write it as a function where x is the interval of convergence, and you write out the power series like this, as we know. And here's summation notation starting at n is equal to 0, but it's not a hard rule that the power series has to start at n is equal to 0, right? It's more about an x minus a, like a common ratio, x minus a to the n, and then a constant factor that's a function of n for each term. That's the nature of a power series. So based on everything just described, power series with a radius of convergence greater than 0, this theorem says that in such a case, any power series is differentiable and therefore continuous over the radius, not including the endpoints. And so, well, we're not proving the theorem in this video, but that's what the theorem says. And so if it's like differentiable, then it's integrable, right, over that continuous interval. And so the derivative f prime of x is, and all you're doing is you're going term by term, and you're differentiating term by term. That's the idea. So the derivative of the series is just the sum of the derivatives of each term. Now, again, I want to state again that thinking about it this way, that we're differentiating each term to take the derivative of the power series, we're only stating that you can think about it this way for power series. Not saying that other series can't be thought of this way, but we're talking only about power series at the moment. This theorem, all of this analysis is for power series. Okay, and so you would, how do you differentiate power terms? Well, that's easy, right? It's the power rule. Bring down the power and then subtract 1 from what the power was. And so it's really easy to differentiate if the general form of, this general form or this general form here. What they do is they bring down the n and subtract the 1 from n. So you have n times c sub n, x, then x minus a to the n minus 1. But then what you notice, though, is that you're not going to have the 0th term anymore, right? If you think about differentiating this is going to go to 0. And you're going to have c1 is going to be the new constant term. So you change the starting point from 0 to 1. Now, there's a couple of things I want to talk about here. And so you're going to see as we work example problems in the upcoming videos that when you're working with summations and power series, you need to be flexible with these definitions in the sense that you need to use your own common sense and logic in a lot of cases. So what I mean by that is, so like you can have a power series a certain power series that the constant term, that there is no constant term. So if we started this, if we decided to start this at n is equal to 1 instead of 0, you could do that. So now there's no c sub 0. So from n is equal to 1 to infinity of this exact same power series, but you're starting at n is equal to 1, that's a power series. Again, what makes a power series is this x plus or minus a to a power. And that power is like increasing each term. and then there's coefficients out front that are constants, and they're just a function of n. That's a power series. It doesn't have to have a constant with no variable term to be a power series, right? And so, like, what I mean by that is you can think about when we get to integration. So we've integrated a power series. So here's the resulting integration, and then you'll see that we can solve for the constant. And a lot of times you solve for the constant of integration, and it's 0. So you're left with the integral of a function is equal to this here. Well, this is a power that we've integrated and gotten a new power series. Well, this power series, if you think about it, this power series doesn't have a constant. Every single term has an x in it. So what if you differentiated this power series? It would be wrong if you differentiated this and then you changed this from n is equal to 0 to n is equal to 1. That would be incorrect. Why? Because you're not eliminating any terms. The only reason you change from n is equal to 0 to n is equal to 1, or wherever, it doesn't have to, the power series doesn't have to start at 0, or like if you were differentiating this, yeah, you could differentiate this, and then you would, since we do have a constant with no x, we would differentiate, use the power rule here, and change from n is equal to 1 to n is equal to 2, right? You do that here, but you wouldn't do that for a power series like this. So you need to, when I say be flexible, you need to just analyze and say, okay, when I'm differentiating, take a look at the power series and see, all right, is the first term a constant with no variable? And that's going to dictate if you update the first term, okay? Now, the next thing I want to talk about is we're going to see examples where we start with we end up like deriving a power series. We come up with the power series representation for functions, and you might start off with something like, so sum from n is equal to 0 to infinity of, let's say it's like a c sub n, so it's just an expression of n to the, let's say, x over 2 to the n. Okay? And so now if we wanted to differentiate this, it's really simple to do the derivative. You're really just coming to the formula here. When you take a derivative of a power series, if you wanted to say d, okay, you're just coming to the formula here, to the a sub n, and you are, just like you learn in differentiation, you're differentiating this with respect to x, but it's easy because it's with respect to x, which means that all n terms are treated as constants. So it doesn't matter how complicated of like all kind of n stuff going all over the place. It's the only variable is the x. That's it. It's that simple. It really is that simple. But however, like, just keep in mind, so if we were differentiating this here with respect to x, okay, well, since, imagine this c sub n is really complicated. There's all kinds of n stuff going on. Well, you just go find the x term and you say, okay, how would I differentiate? All I'm differentiating is this here, because everything else is like constant in front of this. So how do I differentiate this here? Well, what would be the derivative of this? The derivative with respect to x of x over 2 to the n. Well, okay, you'd say n, bring down the n, times x over 2 to the n minus 1, but then just be careful because now we need to use the chain rule, times the derivative of this. What is the derivative with respect to x of x over 2? It's 1/2. For the general definition of the power series, there is no chain rule, even if you have an x minus 3 or whatever, because if you did the chain rule, what's the derivative of x minus a with respect to x? It's just 1. So for the general power series, there's no chain rule involved. You just do like it says here, bring down the n minus 1, and you're done. Here you would have this 1/2 factor, so you have to be careful. You have to remember that. But then what would be the a sub n derivative? Then just whatever the c sub n is, no matter how complicated this is, would just be multiplied in. And then you would do, so, okay, what's the first term? When n is equal to 0, you've got the x goes away. When n is equal to the first term, n is equal to 0, there's the x term vanishes, so the first term is just a constant with no x. So you would update this. You would change this from n is equal to 0 to n is equal to 1, and that would be the derivative. Okay? Now, the next thing I want to talk about is you might find it intimidating. So if you have, so we're going to have examples where you have something, say, like this. Okay, so you want to differentiate, let's say, and it's just weird to think about that. So, okay, I'm going to bring down, what am I bringing down? And what am I subtracting 1 from? Am I replacing the n with n minus 1? Well, no, remember these n terms, for each term in the series, the n terms end up being constants. The x stays a variable unless you specify a number, but the n terms are constants. So you for the power rule, you bring down this entire constant. So you've got c sub n times 2n plus 3 times x, and then you subtract 1 from this entire constant, just like that. This is a constant term, so it's 2n plus 3 minus 1, 2n plus 2. Okay. Now, do we change n is equal to, from n is equal to 0 to n is equal to 1? Well, okay, let's look at the first term. So when n is equal to 0, you still have an x term. So you don't change this to n is equal to 1. You leave it as 0. But there's, if you notice, there's something interesting comes up here. So yeah, when n is equal to 0, you can see the first term is not a constant. It has an x in it. But okay, maybe there's another term that's not the 0th term or the first term that ends up being a constant. And we need to account for that, because if you don't eliminate that, the idea is we'd set 2n plus 3 equal to 0. So 2n is equal to minus 3, n is equal to minus 3 halves. So, okay, this is not even an integer, so it doesn't matter in that sense. But also it's negative, so it doesn't matter in that sense. But, maybe if this was a 4, 2n plus 4, then we would have gotten n is equal to minus 2, but it's still negative, so it doesn't matter. So in that case, the only term that we had to look at was the first term. The first term wasn't a constant, so this is the derivative. We're done. Okay, but still though, but what if we had this? You might be wondering, well, what about like if this was like a quadratic, 2n squared plus whatever? No, you can't end up with a quadratic, because then it's not there's no way there's no power series. Like you'll see that getting a 2n minus 4 like this, it comes from because when you're going to see in the examples, you're creating a function, a power series representation for a function, and you end up creating the power series, and then you have like an x squared outside, and then later you brought that in and combined it with the x. And so, but that's where like you might have brought in an x. Here we would have brought in an x to the minus 4. But if you're going to have like a 2n squared or n squared, well, then that needs to come from inside the series, because you have an n tied to it. And there's no power series. There's no raising x variables to like n squared, right? Or it's not a power series. You see the difference? There's no way for us to create like an x to the n squared minus 3n plus 2 that is rooted in this general definition of a power series. Okay, but still though, what about this? So we have c sub n times 2n minus 4 times x to the 2n minus 4 minus 1. That's it. So 2n minus 5. Okay. First term is when n is equal to 0, you still have x. And I guess technically that's not a power. This is not a power series. So maybe you're not allowed to, if you had, 1 over 1 minus x with x to the fourth here. The idea is when we make power series representations of functions, you can think about doing this. Well, we can turn this into the power series, the geometric series with first term 1, common ratio x, and then bring this in as a multiplier, and that's how you would potentially get something like this. But I'm not sure if that's allowed. Well, okay, this is how you would think about it, though. You still could analyze it this way. So, yeah, the first term has an x in it, right? The first term has an x in it, and as equals 0, you have x to the minus 4. Okay, but if we solve for when n is equal to 0, we see that, or when 2n minus 4 is equal to 0, we see that it's when n is equal to 2. So what's happening is, so this isn't, you can't have a power series with negative exponents on the x. So this really what's happening is this doesn't turn into a power series until n is equal to 2. So really what you would need to do, technically, we haven't learned to differentiate anything but a power series. So this step here, taking the derivative of this, was incorrect because this isn't a power series. It only starts as a power series when n is equal to 2. So what should have been done is this. You say, okay, what's the 0th term here? You've got c sub n, and you would, c sub 0, and then x to the minus 4. Okay, what's the first term? C sub 1, x to the minus 2. Then now this is a power series because you've got you have an x term with these greater than or equal to 0 integer powers. This is a power series. This wasn't. And so now if I can differentiate this, and what does that mean? I do and then I differentiate the power series. And now what do you get here? What is this derivative? This is c sub n, 2n minus 4, x to the 2n minus 4 minus 1. Now you say, what's the first term? Well, n is equal to 2. You've got the first term is 0. Well, it's not 0, but the x goes away. It's just c sub 2. So you do update this. And then here you've got just do regular differentiation. So, because like these are not functions of n anymore, the c sub 0 and c sub 1. So you've got minus 4 c sub 0 x to the minus 5 minus 2 c sub 1 x to the minus 3. And now this is the derivative of this. Now, just to note, if you think about it, it won't ever be the case where if you have a power series, if it is a power series, and you've got some expression of n to the power of x, well, okay, it's always going to be linear, like we talked about. But for a power series, it'll never be the case that you're going to have some value of n other than the starting point being making that the exponent on the x equal to 0. Because if that's the case, then the n's before that would make the integer negative, and it's not a power series. So once you're sure you have a power series where you don't have any exponents on the x that are less than 0, then you know that all you have to think about is, does the first term result in the x is getting eliminated? Because every other term after that's you're gonna have variables or x's. Okay, now integrating a power series. It's the exact same concept as differentiating a power series in the sense that this is the integral of this here. So what you're doing is, it's just like differentiation in the sense that you're coming to the a sub n and you're integrating this a sub n with respect to x and treating everything else as a constant. All the n terms are constants. So like you could bring the c sub n out of the integral. But you just like differentiation, you want to keep in mind that, so here they do the power rule of integration. So it's just x minus a to the n plus 1 over n plus 1, and you're done. But if you've got something like, if the x term, like if this was 1/2 x minus a, then you're going to need to do a substitution. You'll need to say u is equal to 1/2 x minus a. And so du is equal to 1/2 dx, etc. Do the integration, then substitute back. But still, very simple. Okay, so you integrate the a sub n, and you replace the old a sub n with the new integrated a sub n. And the summation, you don't update. You never update the starting point, because you're not eliminating any terms with integration. You never eliminate any terms. What if you think about with integration, all the terms stay, and then on the back end you add a constant of integration. And so what you do is out here you put the constant of integration. So the integral of this power series is this here, and then you put the plus c here. Okay, now when it comes to, you can evaluate, like you're not done yet, because you can actually evaluate what the constant's going to be when you integrate a power series. And you do that because you can set x equal to any value you want that allows you to solve for c. And so what's important to keep in mind is that when you're integrating a power series, there's always, you've got two sides of the equation typically. Well, okay, if you're just integrating a power series and that's all you have as a power series, you don't know if that's equal to a function, well then you just integrate it, you have the plus c, and that's all you can do. But if you actually know that, if you're starting from a point like this and you have a function that's equal to a power series and you're integrating both sides, then what you can do is at the end you can plug in x. So, and you plug it into the power series and you plug it into the function. You could plug it into if you actually have the integral of the function, like you evaluate the integral. So you have a new formula, like, we could integrate 1 over 1 minus x. So now you integrate this and you have a formula for the integral, and that there would be a plus c when you integrate it, but that would get tied up with this. So you could actually plug that in here, plug the x in here, plug the x in here, and now you have an equation you can solve for c. Now, when you plug in x into the power series, you're going to want to pick the center of the power series. Why? Because you need all of the infinite terms to go away to make this work, right? There's infinitely many terms, and the only way to make this work, to get something finite, is to plug in a value that eliminates those infinite terms. That's going to be the center point. So you plug that in, you get the constant term. Well, there would never be a case where you integrate a power series and every term is going to end up having a variable in the entire power series. So you plug in the center point, it's going to be 0. Okay. Next thing to talk about is, so every time you integrate or differentiate a power series, the resulting power series that you get is going to have the same radius of convergence as the original series. Okay, the radius of convergence of the power series in equations 1 and 2 are both r. Right? This is, we differentiated this, we got this. We integrated this, we got this. The radii of convergence of both of these are the same as this. Now, that doesn't mean that the intervals of convergence are the same, because you need to check the endpoints could potentially be different. But the radii of convergence are going to be the same. Okay? Now, one thing to keep in mind, though, is that, so we're going to be working problems where we find power series representations of functions, and like we might have something like, so x cubed over 1 minus x, and then what we do is we write it, we take out the x cubed, and then we can do a power series representation of this function, and then, which is, so that's going to be, but like, okay, we didn't differentiate or integrate, but like it'll be like this, but like we'll the way it works is we might have x cubed times natural log of 1 minus x. So like when you differentiate this, you get a form that we can make a power series out of. So like we end up finding, we get this as a power series. So we have this here. Then we integrate this to get the power series representation of natural log of 1 minus x. Then we bring x cubed inside that series. Now we've got the power series x cubed times natural log of 1 minus x. And that's it. And so what we got, you'll see how we work these examples, but what I'm trying to emphasize here is that when you're differentiating and integrating power series, and then you come in after and like you bring in an x cubed into the series, well, now you've changed the series. It's not, you can't say that the radius of convergence is the same as what you originally differentiated or integrated anymore once you've like brought in an x cubed from the side and like mix that in. So you have to be careful with that, right? I can't take, so I've got this here. We've got this here. I can't integrate this to get, I guess that'd be natural log of, or minus natural log of 1 minus x, then integrate the corresponding, at the same time integrate the corresponding power series for 1 over 1 minus x. So then, and once I've done that, I know that those two have the same radius of convergence based on this rule. Okay, but then I bring the x cubed inside of that integrated power series and mix that in, and now I can't say that, oh well, they still have the same radius of convergence. I've changed things. It's not the same series anymore. I'm gonna have to do the ratio test to find the radius of convergence. Okay, last thing to talk about. So I mentioned that with power series, we can think about this as like you're differentiating each and every term of the infinite series, all infinitely many terms, and same thing with integrating. We're just talking about power series though. We don't branch out this theorem, don't branch out into any of these theorem properties to other types of series. You have to consider those separately. But this is how you can, as far as notation, this is how you can think about taking the derivative of a power series. So here's, you have the entire series and you just put it all in brackets and take the derivative, and you can move the derivative inside of the summation. And then same with integration. You do the integral of the entire series with the dx on the outside, but you can move that integral inside of the sum and put the dx here.